RSA, an acronym that comes from the surnames of Ron Rivas, Adi Shamir, and Leonard Adamant, is one of the first practicable publicly crypto systems described in 1977. Security of it is based on the intractability in factorizing its modulus n into its two respective large primes, both of which are at least 512 bits long. Being able to factorize n will allow attacker to recover the decryption key D to decrypt the encrypted message. It is still being used up to today and is widely used to secure data transmitted digitally in public. It ensures source authenticity, integrity, and confidentiality of digital data. Modern application of it can be widely seen being deployed in web browsers to secure web traffic, used for email privacy, and also used for securing credit card payments. To summarize, RSA is the common choice for applications whenever it concerns the security of digital data. In this project, it will cover attacks targeting small private exponent and partial exposure of primes. For attacks on small secret private exponent, if the private exponent D used is less than 1/3 n to the power of 1/4, it will be susceptible to Wiener Theorem attack. For attacks on partial exposure of secret primes, if there is log 2n over 4 bits of one of the primes being exposed, it will be susceptible to the Crohn's approach to Coppersmith theorem attack. For this project, I have implemented a program to recover the secret decryption key. This program can be used for penetration testing for developers to find vulnerabilities relating to RSA. The programs will take only at most minutes to run and execute. Before we start, there are a few RSA equations to note as we will be discussing it later throughout this video. There is the encryption equation, decryption equation, the Euler-Thomson function, and the equation to generate the Euler's phi function, as well as the equation to generate n with its respective primes. Wiener theorem attack works when private exponent D is less than 1/3 n to the power of 1/4. Given the public key E and n, we will be able to compute the private exponent D by computing the continued fraction expansion of E over n. Next, we then attempt to find the private exponent D in one of the convergent of the continued fraction expansion. To determine which convergent is the one that contains the private exponent, you have to first go through a list of checks. In each convergent computed, you have 4 checks to test. All of the 4 checks must pass to be the correct one for the private exponent. First, you have to check whether the private exponent is an odd value. Then, you have to check whether the Euler phi function is a whole number, and also you need to check whether this equation is more than 0. Lastly, you need to check whether n is the product of the potential primes obtained. For partial key recovery attack that uses Crohn's approach to Coppersmith theorem, it works when there is an exposure of log 2n over 4 bits of one of the primes. For this attack, first we compute the other prime using the exposed prime and n. We then form a polynomial equation as our relaxed RSA problem for us to solve. This equation will be manipulated in a way that it can be expressed into a full rank lattice, so we will be able to easily find the determinant of this lattice later. Once we got the lattice, we then perform the Lenstra-Lovesh basis reduction algorithm on the lattice to get the reduced polynomial equation. We then attempt to solve this reduced polynomial to get the roots, and these roots are the primes that we are looking for. Now, I will be showing you demos of the attacks in this project with some of the test cases used during experiment.